So we're finishing up on the last little bit of this voting and weighting voting system in chapter 2. And today we're pretty much just going over some definitions of things that we actually were doing when we were looking at the Bonds-Off Power Index. We had to look at different coalitions or subsets of our groups. And so we're going to look at that, how to find subsets of sets. And then when we were looking at the Shapley-Shubik index, we were looking at sequences and how order of coming into a coalition was important. And so different order mattered. And so those are actually called permutations. And so we're going to look at permutations of sets and how to count permutations. And then using that can be helpful when we were looking or finding the index of those different weighted voting systems using those different methods. So our plan is to finish this chapter 2 today, and then we're going to, on Wednesday, I'm hoping to do a in-class exercise all day where we kind of look at the different methods that we were looking at with voting, how you can vote, and then looking at different weighting voting systems and using activities to kind of show those in play. So I probably won't lecture, or not, I won't lecture as much, but I won't be videotaping Wednesday's lecture as much. So if you miss that lecture, then I might have a different activity for you to do if you can't make it to class, or it's possible you just can't make up those points. The other thing is that we're at the point of the semester where I wanted you guys to have some sort of a say of what we're going to learn next. And I had done this last semester when I taught this course for the first time. We went in through the voting methods, and then I had students look at the different topics. So I broke you guys up. It was basically an assignment on Canvas where you went in, first come, first serve. You chose a topic, one of the topics we could cover in this course. And then you went and you did a little bit of research and found out what that topic entailed and what we might be looking at to give the class a general idea of what that topic is about. And then once you guys did your little bit of research, the students came back, and you guys will too, and kind of give a little overview, very quick overview what that topic is. And then we'll have a chance where we'll go in and we'll vote, and using some of the voting methods that we looked at to decide what we're gonna teach on next, or you're gonna learn on next. And I might be learning on this with you on the side right before I come in and lecture, because some of these topics I haven't seen for a while or I've never seen before, which is kind of, for me, an awesome, cool course, because I'm learning things with you. Anyways, so I just wanted that to be said, and now let's jump into the last part of this section. Actually, while I'm getting up the screen to share with you, maybe I can try to do two things at once. So because we're almost done with the second chapter, we will be having a test soon. My guess is that it's going to be not next week, but the following week. So probably Monday of that following week. So 21st, so that would be the 28th. And I'll post that too on Canvas that's coming up and what it will cover, which would be chapter 1 and chapter 2. Okay. Other thing is I'm going to try this other platform for writing my notes. So hopefully this works maybe better than before. Okay. Okay, just gotta manipulate everything again. Once I share it, everything kind of hides. And I don't want to hide your faces because I just got to see some of them for the first time. Okay, so let's jump into what a subset is. Grab my pen. Shoot. I wanted to rotate. Of course, that changes it. Sorry. I was running so slow earlier. Okay, so once again, so a subset. The set is any combination of elements from a set. Okay, so a couple things to know is that the empty set and we denote that with curly brackets with nothing in it. Sometimes you'll see it with a kind of a zero with a slash in it as another way that you might see it, notation. This is a set. No elements. And this is considered a subset of a set. This is considered a subset of a set. Also, a set with all the elements in it is also considered a subset. So a set containing all elements of a set is also considered a subset. Of a set. Okay, so if you're looking at a coalition, it really doesn't make sense if you just have one voting member, right? If there's just one voting member, you know, they either make the decision or don't make the decision. But let's look at if we had a coalition that has two voting members. So let's say we have player 1 and player 2 are voting members. A voting system. If we wanted to look at the sets, let's look at all the subsets. Player 1 with player 2. So subsets. Empty set, this is a subset. The subset that just has player 1, that would be a subset. The set that just has player 2 in it, that would be a subset. And the subset that has player 1 and player 2 in it is also a subset. So with 2 players, or 2 elements, set with 2 elements. Has 4 subsets. Okay. Let's look at if we were having 1 extra player. So if we add 1 more player, find all the subsets. So now we're looking at all the subsets if you have player 1, player 2, and player 3. Well, basically, when we look at all the subsets, with just adding 1 additional player, that would include all of these sets. So we would include the sets without player 3, because those are all subsets. So we already found those, player empty set, player 1, player 2, and player 1, player 2. Let's go in here now, and let's just add in player 3. So it's all these sets plus, so if I just plugged in player 3 into this empty set, that would now give me the set which is player 3. If I look at the set which is player 1 and I add in player 3, this would give me another subset with that extra player. I could have the set which is player 2 and then player 3. Or I could have the set with all players. Now it would be player 1, player 2, and player 3. So if we count this, so a set, this has 3 elements, 3 players. So a set with 3 elements has how many subsets? So 1, 2, 3, 4, plus another 4, so it has 8 subsets. Notice if I continue in this order, so let's say now you want to find all the subsets that occur if I add 1 extra player. So find all subsets. If we add player 4. Well, that would include all the sets that we had with just these 3 elements, player 1, player 2, and player 3. And then we can find the other additional ones by plugging in player 4 into the ones that didn't include player 4. So we could list again all the 8 we just found before. The empty set, player 1, just player 2, player. I'm going to just add it so that it's kind of consistent with a number going up. Player 3 was just a set of 1. Then we had player 1, player 2. We have player 1, player 3. We had player 2, player 3. And then, did I get them all? And then we have player 1, player 2, player 3. Yep. So these are all sets without player 4. But now if we took these and we added in player 4, those would give us all the subsets with 4 players. And so if I just added them into the empty set, that would just give me player 4. So that would be a subset. I could put it in with just player 1. So that would be player 1 and player 4. I could put it in with just player 2. So player 2 and player 4. Player 3 and player 4. Now I'm at player 1, player 2, player 4. Player 1, player 3, player 4. See how just adding one additional element each time is getting a lot. So player 2 and player 3, and then player 4. Player 2, player 1, player 2, player 3, and player 4. With all of the elements. So basically, adding in that additional player just doubled what we had above here. When we had 2 players, adding in that additional player doubled what we had above here. And so if we look at this, double of 8, and if you count through this, a set with 4 elements, has 16 subsets. So we can reason a set within elements has 2 raised to the nth power subsets. So using this, we could find how many subsets that any number of elements in a set has. Do I want to list them? Probably not, but I can find them. So how many subsets would there be for a set with, let's say, 7 elements? So according to this, we would look at 2 raised to the 7th power. So that tells me I'm looking at 2 times 2 times 2 times 2, 7 times. Let's just kind of group this and go down, and we can figure it out without a calculator. Well, we know 2 times 2 is 4. Grouping those 2 times 2, that would be times a 4. Grouping that 2 times 2 is a 4, and times that 2. So 4 times 4 I know is 16. And that's times 4 times 2, which is 8. 16 times 8. 6 times 8 is 48. I'm going to carry my 4. 8 times 1 is 8 plus my 4 is 12. So 128 subsets. Okay, so that would be kind of hard and long to have to list all that out. But when we're talking about the Shapley-Shubik method, there's a couple things that don't make sense. It doesn't make sense to have a coalition that has no players voting for it. Actually, and I'm not talking about the Shapley-Shubik. Shapley-Shubik was where orders mattered, and it mattered when you came into the coalition. We call those sequential coalitions, but when we were looking at the Bonds-Off Tower, it didn't matter what order you came into the voting method. It mattered if you were pulled out of the voting method, were you a critical player or not. So for the Bonds-Off Tower, we looked at subsets of the different voting coalitions. Okay, so again, note a set of 0 players well, that's never going to be a winning. When we're looking at the Bonds-Off Tower, we were looking at all the different winning coalitions. And so a set of 0 players is impossible to be a winning coalition. So if we're looking at the number of possible coalitions, with N voters, we're going to look at 2 to the nth power minus 1. So we're getting rid of that empty set. That would be impossible to be a coalition. Okay, so let's jump to an example. Okay, so let A be a set with 10 elements. So usually you'll see sets with a capital letter. So it says let A be a set with 10 elements. So part A, we want to find the number of subsets of A. Okay, so we know the number of subsets is equal to 2 to the n. And we know what n is. And in our case, n is equal to 10. So we know that we're going to have 2 raised to the 10th power. So that's kind of cool. Don't want it now, but that's kind of cool. Go away. There you go. Okay, so we could go out and we can multiply this out 2 to the 10th time. Didn't we just figure out what 2 to the 8th was? Maybe that was 2 to the 6th. That was 2 to the 6th. Rules of exponents. This is the same thing as 2 to the 6th times 2 to the 4th. I'm just going back to rules that if you have the same base, you add your exponent. So I was kind of going reversal to what I knew. So I knew what 2 to the 6th was. We just found that. That was 128. All times 2 to the 4th. So 2 times 2 is 4, times 2 is 8, times 2 is 16. And to save time, we could multiply that out. But 16 times 128, that's 2,048. And then part B, find the number of subsets of A having 1 or more element. One or more element.
Professor, for part A, we did what 2 to the 7th was, not 2 to the 6th.
Oops. Thank you. I might have done that wrong then. Up here.
It's 1024.
Let me just make sure I got that right over. So 2 to the 7th is 128. Okay. Thank you. So this would have been, gotta erase it. 2 to the 7th. And then this would have been 2 cubed. And 2 cubed is 8. It would have been 128 times 8. Which was 1,024. I don't know why. Okay. Why is it doing that? Thank you for catching that. So find the number of subsets of A having 1 or more elements. So this is actually really useful when you're looking using probability. A lot of times we're counting things, and we might do probability in this class, we might not. But to count the number of subsets, this is saying having 1 or more element. And so basically, this is talking about the complement. So this is looking at excluding the set of having no elements. If I looked at all of the sets and I just excluded the one that didn't have any element, any of the sets I looked at then would have at least 1 element in there or more. And so I know that the number of sets only having no elements is there's only one set with that. So there's only one of these. So if I look at, there's 1,024 subsets minus the one that has nothing in it. This is going to equal 1,023 subsets of having one or more elements. So when we're looking at all the possible subsets, when we're looking at a voting coalition, again, it doesn't make sense to have nobody in that voting coalition. And so a lot of times we'll just exclude that. But what if it said, find the number of subsets having exactly one element? Find the number of subsets of A with exactly one. Element. Okay, well, only one element, well, that would be the case where it was just player one, or that would be the case where it was just player two, or that would be the case with just player three. If it's just one element, and if there's 10 different players, then there has to be 10 different sets with just one element. So these are the sets, all the sets with just one element. So that would mean in our case, so a set with 10 elements would have 10 subsets with just one element. Really what this is getting at, if we're talking again about voting coalitions, it wouldn't really make sense to have just one player going in there and making it a winning coalition. If one player could go in there and make that a winning coalition, then that means they're a dictator. And it wouldn't really make sense to have a dictator for voting. And so a lot of times when we're looking at the number of coalitions, we're getting rid of the subsets of having no players, and we're looking at getting rid of the subsets that have just one player. And so the last question asks, find the number of subsets of A having two or more players in the element. So find the number of subsets of A having two or more elements. In the subset. Okay, so we know that there was 1,024 subsets. Minus 1, which was the empty set. then if we subtract off 10, which were the sets with all one, subsets with one element. That would give us sets that would have 2 or more. So 1024 minus 1 is 1023. 1023 minus 10. So that would be 1013. So this would be the number of subsets with 2 or more elements. Or more. Okay, so we can take it a little further. So, this is asking, so find the weighted voting system with 10 players. So it says, let me reread that. For a weighted voting system with 10 players, find the total number of coalitions. We basically just did that information. So we have 10 players, and the formula was 2 to the nth minus 1. So this is the number of possible coalitions. Within players. Because we had to take off that empty set, because that doesn't make sense for a coalition. And so in our case, we would have 2 to the 10th minus 1, which we found to be 1024 minus 1, which is 1023. And then it asked us, the next part says, find the number of coalitions with 2 or more players. Sorry, I'm in class. Talk to you later. You need to answer that to turn it off. Find the number of coalitions with 2 or more players. Okay, well, we just did that. Basically, we found it with one or more player. So let's subtract off all the one player coalitions, which is not always going to be equal to n. So in our case, we're going to subtract off 10. So we would have 1,023 minus the 10 players. So this is going to equal 1,000. One more. So consider a weighting voting system with 6 players, player 1 through player 6. Okay. So we have a weighted coalition with 6 players. A, find the total number of coalitions in this weighted voting system. So again, that's going to be 2 to the nth minus 1. Well, in our case, it's 2 to the 6 is our n value minus 1. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So 2 to the 6 is 64, minus 1, which is 63. Okay, so we have 63 different coalitions we could have. So part B, how many coalitions in the weighted voting system do not include player 1? So how many coalitions in this weighting voting system does not include player 1? Hint. They give us a hint. Think of all the possible coalitions of the remaining players. Okay, well, if we looked at all the coalitions, let's think of it. All the coalitions without player 1. Well, wouldn't that be, and I could have said that P is 1, wouldn't that be where we had 5 players? So it would be the subset. Coalitions with 5 players. So if we let n be 5, And we looked at 2 to the n minus 1 for 5 players. This is 32 minus 1, which is 31. So here's 31 coalitions without player 1. Part C, how many coalitions in the weighting voter system do not include player 3? So how many in the weighted coalition do not include player 3? Well, I can do the same sort of reasoning. It didn't say didn't include player 3 and player 1. It just said how many would be there without player 3. So if I looked at all the coalitions and just removed player 3, that would mean I'd have player 1, player 2, player 4, and player 5, and player 6. We have 6 people, right? And so there would still be 5 players. So I can think of it the same way. 5 players. So I would have to have 2 assists, plus I'd have to get rid of the case where the empty set. And so again, I would have 31 possible coalitions without just player 3. Then it asks me how many coalitions in the weighted voting system do not include both player 1 and player 3. Okay, well that's a little different because it's saying does not include both of them. That's a good question. And then let me just go down. And the next one, which we need to find D, says how many coalitions in this weighting system include a piece of 1 and piece of 2. to use the answer for part A and B. Okay, let's kind of think about this. So how many coalitions in the weighting system does not include P sub 1 and P sub 3? Well, if we excluded P sub 1 and P sub 3, I'm just wondering if it's both of them. I might have to come back to this one on Wednesday. I'm going to come back to this one on Wednesday. I don't want to guide you wrong, and I need to think about that. Let me come back to that one. Okay, so let's jump into the next piece, which is permutation. Okay, so this has to do with the Shapley-Shubik index. And remember, we were looking at all the sequential coalitions. So we were looking at it with all the members playing and the order that it was that they came in. The order mattered here, where order did not matter. Didn't matter the order they came in the coalition for the bonds off power. So for permutations, permutation, see the definition of a set of objects is an ordered list of the objects when you change the order of the objects, you get a different permutation. So changing the order gives you a different permutation of the objects. Okay. So number of permutations in objects. In Factorial. And so we looked at this before. This was the same thing as taking your number n, multiplying it by n minus 1, multiplying this by n minus 2, and going down until you got to 1. Okay. So if you were looking at the following, solve the following without a calculator. if they were asking you to find 19 factorial, if you're given that 20 factorial is equal to, oh my, I don't even know if I know how to read this number. So 2, comma, 432, comma, 902, comma, 008, comma, 176, comma, 640, comma, 000. Thousands, millions, billions, trillions. Then I don't know what was after trillions. Quadrillions, quintillions. I have no idea. But it's a huge number. Now, how do you think we can do this without a calculator? Well, 20 factorial. If I was to write this, this is the same thing as 20 times 19 times 18 times 17 times 16 dot 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 times 3 times 2 times 1. But notice that this right here is 19 factorial. So technically, I could write this. This is the same thing as saying 20 factorial. This is the same thing as 20 times 19 factorial. Or I could say, let me just grab it so I don't have to rewrite this number again. 20 factorial, oops. $20 factorial was this number. I can grab that. So I can say if this huge number is equal to 20 times 19 factorial. And this is equal to 20 all times 19 factorial. So if we divide both sides by 20, we would get 19 factorial by itself. Okay, notice that they both are divisible by 10. So I can cancel out a 0. And this is also divisible by 2. So 2 goes into 2 once, 2 goes into 4 twice, 2 goes into 3 once with a remainder of 1. 2 goes, and am I doing this right? Yeah. 12 6 times. 2 goes into 9 4 times with a remainder of 1. 2 goes into 10 5 times. 2 goes into 2 1. 2 goes into 0 0 times. 2 goes into 0 0 times. 2 goes into 8 4 times. 2 does not go into 1, so 0. But it goes into 17 8 times with a remainder of 1.
2 goes into 16 8 times, 2 goes into 6 3 times, 2 goes into 4 twice, 0 0 times, and then 2 more zeros. Not a calculator, and if you plug that in a calculator right now, my guess is that might give you an error. I don't remember where this is on my calculator. Yeah, I don't know where it is on my calculator. I used to. I'd have to find it. Okay, so same sort of kind of reasoning like we just did. We can evaluate things without a calculator with huge numbers. So if you had had 201 factorial, and you would get an error if you plug that in the calculator. It's so huge, all over 199 factorial. Again, it wants you to simplify this without a calculator. Well, if we go with the definition of what the factorial means, we're just multiplying the number by itself, decreasing by 1 each time. So this is really 201 times 200 times 199 times 198, all the way down until we get to 199 factorial. Well, that's 199 times 198 times 197, all the way till we get to 1. Strictly multiplication in between, we can cancel like factors. So 199 they have in common, 198, 197, all the way down until they get to 1. So technically, 201 factorial divided by 199 factorial is just equal to 201 times 200. So if I just add the zeros for my 200 and then multiply 2 times 201, that would give me my number. 40,200. The same sort of idea. If we had 11 factorial all over 8 factorial, this is the same thing as 11 times 10 times 9 times really 8 factorial. Another way to write it, all over 8 factorial. So this is just left with 11 times 10 times 9. So 10 times 11, 110 times 9, which gives a 990. So if you had a weighted voting system, with 7 players, Find the number of sequential coalitions in this weighted voting system. How many sequential? So this is where you need to be careful. Coalition. This is where we were looking at it with all the players coming in, but the different orders that is possible in this weighted voting system. This is where we look at n factorial. In our case, we're looking at 7 factorial. So 7 times 6 times 5 times 4 times 3 2, times 3 times 2. I don't remember where this goes on here. Okay, I remember. If you have the TI 30XIIF, if you go to probability, and you scroll to the left 3, you'll see a factorial. So I plug in 7, and then I go to the probability, scroll to the left to the exclamation mark. I get 7 factorial. So this is where it's giving me scientific notation. It's saying 5 point. Let me see if I can get out of there. It was giving me scientific notation. It was saying 5.040, I believe, times 10 to the third power. My calculator setting was. That 10 to the third tells me to move this number over 3 spots. So this is 5,040. So if I had 7 players and I wanted to write all the different coalitions out, I'd have to write out 5,040 different ones. Number of sequential coalitions. So how many sequential coalitions in the weighted voting system have player 7 as the first player? Well, let me give you a rule. If you're looking at the number of sequential coalitions with player P in a fixed position, you're looking at the number of possible coalitions, sequential coalitions, with player P. In a fixed position. Equal to n minus 1. So if we want to figure out player 7, how many places they are in the first, as a first player, then we're looking at n was 7 on our case. And so we would have 7 minus 1 factorial. Which would be 6 factorial, which would be 5,040 divided by 7, which is 720. 720 positions or sequential coalitions with player 7 in the first position. Okay, so this is a perfect place to stop. So I did not finish all of this. I want to go back and look at those couple problems I didn't get to and said I would come back to on Wednesday, and then maybe do a couple more problems with the permutations, and then we'll start on the activity I wanted to do. We might not get through all of the activity, but we'll do a couple different exercises and different coding and look at that, and then maybe finish up on that on Monday. So let me stop here. I do have office hours right now, so if you want to stay, then you're welcome to stay behind.